In this little video, I'm going to tell you a little bit about constraints in molecular dynamics. We know that the fastest degree of motion in MD simulation is the vibration of a bond that contains hydrogen. And because this vibration takes place on the order of, let's say, 5 to 10 femtoseconds, my integration time step is limited to 1 femtosecond. However, for many of the phenomena that we will be looking at, such as the properties of membranes or the unfolding and folding of a DNA helix, we are not interested in the vibration of this bond. So what can we do? We can fix the bond length of this bond. Or, in other words, we can solve the equations of motion under the constraint that the bond length between x and h is fixed. The simplest example that you can take from mechanics, and I think this is discussed also in the book, is a block falling on the ground. If this block is directly falling on the ground, you can solve Newton's second law for it, a simple differential equation, and that will give you the mechanics, the positions and velocities of this block. However, if the same block is now moving on an inclined plane, then the movement of the box is constrained by the inclined plane. Similarly, in my MD simulations, the movement of these atoms is constrained by the fact that the bond length between x and h is fixed. Solving such equations in the presence of constraints is done using something called Lagrange multipliers. This is information about this is provided in the beginning of the book, and some of you may remember it from your math courses. So without going very deep into the math, one can write that the constraint force, so when the bond length between x and h is constrained, there is an extra force on every atom because of the constraint. And this constraint force, let's say because of constraint number 1, because this atom may be bonded to, let's say, another hydrogen atom. Let's say this is constraint number 1. The constraint force on atom x, because of constraint number 1, is given by some Lagrange multiplier. So this we shall call 1, and the partial differential of the position of atom x, with respect to the position of atom x of the constraint itself. And the constraint can be written in the following way. So the constraint between atoms 1 and 2 is written like this. So the distance between the two atoms So what this equation says is that the distance between the two atoms is fixed to a distance d. So this is how a constraint is written, and this is the force on atom x because of one constraint. If there are multiple constraints, there will be more forces arising out of constraints only. There are also other forces arising out of standard interactions that have not been written here. So the equations of motion get modified as follows. For any particle I, according to the Verlet integration scheme, this is what the equation of motion looks like. T minus delta t. So the positions at time t minus positions at time t minus delta t, plus the acceleration, which is all the forces on particle I divided by the mass. So this is from the Verlet scheme. When you use Lagrange multipliers, then the new positions are slightly different, and we'll call them prime. And they are different because of the extra forces that arise because of constraints. And this is given by the old positions without constraints, plus the change in the positions because of all the constraint. Let's say this particle I is under k constraints. So for example, x is under 2 constraints, so k would be 2. And for each constraint, there is a Lagrange multiplier. I will derive this equation in a little bit. I'm just writing the overall equation to give you an idea. So these are the changes in position arising from k constraints. Here Ri is the particle in question and J's are the particles with which there is a constraint. So for example, in this case, J would be this first hydrogen and the second hydrogen, K would be equal to 2. So let's take a few minutes to derive these equations. How do you come to these equations? And to do that, we will take the simple case of a simple diatomic molecule. So you look at two particles 1 and 2 which have a bond length of r, let's say, what do I use in my, which have bond length of d12. So my constraint of course is that the distance between r1 and r2 is restricted to the bond length, to the equilibrium bond length, and this constraint is written as a sigma. Right. Now the force because of the constraint on atom 1 is given by a Lagrange multiplier multiplied by a partial differential of the constraint with respect to the position of atom 1. And based on this equation, you can write this as the partial differential of r1 minus r2 squared minus d12 squared. And if you simplify this, what you get is 2 lambda into r1 minus r2, which is simply equal to 2 lambda r12, where r12 represents the distance between r1 and r2. This 2 lambda I am going to write as lambda 12 for simplicity. You can do something very similar for particle 2. The constraint force on particle 2 will be equal to the same Lagrange multiplier, and now the partial differential is taken with respect to the position of particle 2, sigma 12, and you can eventually show that this is equal to minus lambda 12 r 12. So this is the constraint on particle 1, this is the constraint on particle 2. So based on the equations that I wrote on the previous page, the final position of particle 1 in the Worley scheme, so this is r1 prime, is equal to r t plus delta t, and r plus t plus delta t and plus r t plus delta t is obtained from the typical Worley contribution. So this can be written as 2 position of r and plus the can you please edit the video so that this part is cancelled where I started with this part. So please edit it until I reach this equation, and then we will stop for a minute. Okay, so Fc1, which is equal to lambda 12 position, the distance between r12, is the constraint force on atom 1 from that constraint, and the negative of that is the constraint force on atom 2. I had written previously that the positions of atom 1 from the Worley algorithm look something like this. This you have seen several times before. T minus delta t plus the square of the time step divided by the mass multiplied by all the forces that particle 1 is feeling. And these forces must now include the constraint force. So this equation becomes 2 r1t minus r 1 t minus delta t plus delta t squared by m multiplied by all the forces that this particle is feeling, which is equal to the forces from bonded and non-bonded interactions plus my constraint force, which is lambda r 2. So this is the modified Verlet algorithm when you have a constraint in the system. This is for one constraint. If you have several constraints, then you have to sum up over all these constraints. And the equation for particle 2 looks very similar. So if you change this 1 to 2, this becomes 2, this becomes 2, 2, and now you have a minus sign here from here. So this is what you can do when you constrain the distance between two atoms. And now it turns out your time step can increase from 1 femtoseconds to 2 femtoseconds. There are various algorithms by which this mechanism is implemented in simulation programs. They can be called shake, which is typically used in the charm force field, settle, this is typically used for water molecules, and in GROMACS we use something called links, which means linear constraint solver. So we use constraints when we are not interested in the certain bond or angle vibrations. So I forgot to mention that you can also constrain the angle between three particles, one of which may be a hydrogen. So you're often not interested in these vibrations either. But even after implementing all these constraints, you can only double your time step and not go beyond that.